moving coil galvanometer. It is a device used to check whether there is any current in a circuit. A sketch of moving coil galvanometer is shown in the screen. It consists of a rectangular enameled copper coil wound over a cylindrical soft iron core. The coil is free to rotate about a fixed axis, to which a spring is also attached, which can provide a restoring torque. A pointer is attached to the coil. Tip of the pointer is on a circular scale which is calibrated. This arrangement is placed in a radial magnetic field produced by two concave shaped pole pieces of permanent magnet. The radial magnetic field has two functions. One is it increases towards the center of the coil. Second is the plane of the coil is parallel to the magnetic field. Now let us see how this coil deflects in the magnetic field. Already we have seen in the previous video that deflecting torque when current passes through the coil, which is in the uniform magnetic field B, is BINA sin theta, where B is the external magnetic field, I is the current through the coil, N is the number of turns, A is the area of the coil. Since the plane of the coil is parallel to the magnetic field, its area vector is perpendicular to the external magnetic field. So theta is 90. Hence, the maximum deflecting torque equal to BINA. Let us call it as equation number 1. The spring provides a counter torque K5 to balance the deflecting torque. Hence, the deflecting torque is equal to restoring torque at equilibrium, and restoring torque is always proportional to the angle turned by the coil, or restoring torque equal to K5. So in order to produce a steady deflection, we say the equilibrium. Deflecting torque and restoring torque are same, equating 1 and 2. See, restoring torque K5 I have marked as equation number 2. We get phi equal to BINA by K. The equation BINA equal to K5, hence phi equal to BINA by K, or phi equal to BNA by K into I, which is equal to G into I, where G equal to BNA by K. G is called galvanometer constant. Now look at this equation. This galvanometer constant depends on certain quantities. What are they? They are the magnetic field B, number of turns of the coil N, area of the coil A, and the torsional constant K. If we change any of these quantities, we can vary the galvanometer constant. Next, let us see what is meant by current sensitivity. Current sensitivity IS equal to phi by I and phi equal to BNA by K into I. Hence phi by I must be BNA by K, which is the current sensitivity. So current sensitivity also depends on magnetic field, number of turns, area of the coil and torsional constant. Similarly, voltage sensitivity. Voltage sensitivity Vs equal to phi by V, that is equal to phi by IR. According to Ohm's law, V equal to IR, or we write it as phi by I into 1 by R. And we got phi by I is equal to BNA by K. Substitute here. BNA by K into 1 by R. This is the voltage sensitivity. Now, how we can define current sensitivity? Current sensitivity is the deflection produced by the coil when unit current passes through it. Similarly, voltage sensitivity is also deflection produced by the coil when unit potential difference is applied to the coil. Now here an important point to note: an increase in current sensitivity may not necessarily increase the voltage sensitivity. Why? The answer is here. We know current sensitivity is BNA by K. Suppose we increase the number of turns. Either we can increase BNA, whatever it is. Suppose we are increasing in case of coil, we are increasing the number of turns. So when N dash becomes 2N, current sensitivity becomes IS dash. That is equal to 2 times BNA divided by K, which is equal to 2 times IS, or IS dash equal to 2 times IS. Current sensitivity multiplies. Current sensitivity doubles when number of turns doubles. Similarly, voltage sensitivity, you just look at this equation, equal to BNA by KR. Here also number of turns we are doubling, N dash equal to 2N. So when number of turns increases, definitely length of the coil increases. That means resistance of the coil increases. If length doubles, number of turns doubles, therefore resistance doubles. R dash is 2R. Here we can see Vs dash, new current sensitivity for 2N number of turns, becomes 2 times BNA divided by 2 times KR. R had become 2R. That is BNA divided by KR. 2 and 2 get cancelled. BNA divided by KR, which is the original voltage sensitivity. So here we had seen, even though we are doubling the number of turns, the current sensitivity doubles, whereas voltage sensitivity remains constant. Thank you.